All right, good morning, class. Today we're going to do the second part of unit or topic 5, and it's actually the last one. So it's only two kind of lectures. First topic or first lecture contained a sub-lecture within it. That was a recording. I already put it on Blackboard before that lecture. That kind of involved lots of derivations. And then last class, we went into, in the last part of it, models, which are based on the excess Gibbs energy, that correlate pressure data of mixtures, where we have the compositions, the X composition and the Y, and given pressure data, to correlate it to the activity coefficient for a given substance in a mixture. So if you remember, the activity coefficient was something we saw in modified Raoult's law. So now what we were presenting is how do we obtain that, what's the values of the activity coefficient given a certain composition in a given mixture. So we saw the simplest form. So this is assuming, we have a constant value. Then the next simplest form, a straight line fit to the data. So what's the data? It was the Gibbs energy, excess Gibbs energy, over RT divided by x1, x2. So that was the equation I presented last class. We're going to see it again in this lecture. But what I'm saying, simplest form, the value of that we assume to be constant. The ideal case, ideal solution, what's the activity coefficient for ideal? 1, right? So modified Raoult's law becomes Raoult's law when the activity coefficient is equal to 1. 1 suffix, constant, 2 suffix, linear line. So this the Redlich-Kister form is basically all of these simplified into one equation where there's a parameter that we can equal to 0, and then it simplifies to these different ones. So again, I would say review those lectures. I can talk a lot about it, but until you see the equations, it won't make much sense. Today we're going to do the Van Laar representation, which is basically the 2 suffix Margulies equation, but flipped. So it's very similar, but flipped. So we'll see that in a second. Then we're going to look at Wilson equation for binary mixtures, then Wilson equation for multi-component mixtures. Then we're going to do NRTL, so non-random two-liquid theory model. And then the universal quasi-chemical model, we're not going to look at that one per se, but that's the one that also exists. All right, so we're going to start off with the Van Laar representation. So this is the representation where initially I was talking about the excess Gibbs energy being on top, divided by RT x1, x2. This yellow line is the plot of the excess energy divided by RT x1, x2, this line here. Fitting that line, right, with a straight line, this is a 2 suffix Margulies equation. Okay, so if you go back up here, it's both the Margulies equation that has the coefficients and the 2 suffix Margulies equations. Same thing, this one and this one. So we plotted that, we got the linear line, and then from that we obtained the coefficients. Now for the Van Laar, instead of doing this plot, what we're doing is we're doing the opposite. We flip it. Okay, so it's just another model, but it's the same idea. So when we flip it, we get the following. Now we have parameter A prime and B prime for the equation, and then we simplify the expression doing some math, we multiply it out. In the end, what we have here is A prime plus B prime is equal to 1 over A prime to 1. And then A prime minus B prime is equal to 1 over A prime 1, 2. Okay? So these are basically the coefficients for the Van Laar representation, and we can get them from the plot, and I'll show you how in a second. So from there, we can write this expression, this same expression, we can flip it over, and we can write it in terms of GE over RT x1, x2 with these new parameters, which are A prime 1, 2 and A prime 2, 1. So why do we flip it like this? Because we're going to use the summability relations that we talked about in the last lecture. That has x1 natural log activity coefficient 1 plus x2 natural log activity coefficient 2. So that's going to equal to this. And from that, we can get what is the activity coefficient based on this model. So just plotting the values of the reciprocal, we get this. And when we fit the straight line, so we get the slope and the y-intercept. So taking this equation, we have this. We find that the natural log gamma 1 is equal to the following. Natural log gamma 2 is equal to the following. So again, you don't need to derive these, but these will be given in the equation sheet. All right, so for the Van Leer representation, this is the two equations for the coefficients, and obviously this is for a binary system, as we see here. So both the Margulies equation and Van Leer are two suffix, you can say, and both of them are empirical models, so they're not really like theoretical based models. So typically we don't use them for multi-component systems, we only use them for binary systems. All right. From these equations, if we have the mole fraction of component 1 approaching 0, so here we see this x1 approaching 0, this approaches 1, we get that the natural log of gamma 1 is going to equal a prime 1, 2. So in a way, similar to Margulies where we were saying if we have a1, 2, we have little 1 and lots of 2. So little of 1, so infinite dilution, meaning x1 approaches 0. Where do we find this on the plot? Right, if you look at, let's go back to like this equation up here. If I have x1 equals 0 and x2 equals 1, right, what do we find in this case? On this plot, where would it be? So this is x1 here, right? So if x1 is 0, then it's going to be the y-intercept. Okay? So if I go back here, 1 over a prime 1, 2 is going to be this point here, my y-intercept. And then the opposite for x2 approaching 0, that means x1 approaches 1, then it's going to be whatever the value is at x1 equals 1 on that plot. All right? So those are the infinite dilutions for 1 and 2, similar to what we had before for the other ones, but the reciprocal. Okay, so the value here, 1 over the value would be what we plug in here. So in Margulies' equation, it was this line here. In that case, we took the parameter as is. So the intercept was the parameter. It's not 1 over. Okay, so you'll see that from the previous lecture. There's another form for Van Leer's equation. So this is the one presented in the last slide. This is another form that avoids division by 0. Why? Because here, in the denominator, I have x2. And if I plug in x2 equals 0, then this denominator is 0. So then I get infinity. To avoid that, this same equation, some math is done to it to rearrange it. So now we have x1 and x2 in the denominator. So if one of them is 0, the other one is there, so you're not going to get 0. All right? So just another equation, another form of the Van Leer representation. All right, so here we're going to repeat the example from last class, but now using the Van Leer equation. Initially, what we were given were pressure data, mole fraction in the liquid phase, mole fraction in the vapor phase. From this information, we derive the natural log of gamma 1, natural log of gamma 2, and then from there, we calculate what is GE over RT x1, x2, which is basically the sum of these two, right? But each one of these is multiplied by x1, x2. And I can go back to the other lecture to show you. All right, so here we have the pressure data, we have the x and the y. So we can see here to get gamma 1 and gamma 2, we use modified Raoult's law. Okay, we do the natural log of that. Then to get this, we take the summability relations, which is the general form is without this denominator here. So the general form is just x1 natural log gamma 1 plus x2 natural log gamma 2. Why do we add this on the bottom? Because we're dividing by x1 and x2. Why do we do that? Because the model is based on that. Okay, so the Van Leer model is the reciprocal of this. So once you do all of this math, okay, and then you divide by x1, x2, right? And why do we have 1 minus x1? Because that is what x2 is. Then you do the reciprocal, so we do 1 over the result. So here you can see the values were like 1.087 and so on. If I go to the other slides, you're going to see how they differ slightly. So here I have the same numbers, but instead of 1 point whatever, now I have 0.920. Okay, so in this case, you plot these 4 points on a graph. So we can see here 1, 2, 3, 4 points. Then we fit them to a straight line. Okay, and then from that straight line, we get the parameters a prime 1, 2 and a prime 2, 1. And then from there, we can use those in my model calculations to find at any given pressure, right, or any given composition, what is the pressure in my system. Okay, so let's show you the next step there. So we have this first column is what we picked, as I want data for a mixture from 0 to 1. And I'm going to take step sizes of 0.1. So that's something I picked. It's like I already built the model using 4 points. I got these 2 parameters. Now my model is done. Now I can use the model to find what is the activity coefficients. So here we find activity coefficient 1 and 2. How do we do that? Using the equations that we presented earlier in the slides. So what do we need here? We need the mole fractions, and we need A12 and A21 prime. You plug them in, you find gamma 1, gamma 2. Then we can find the pressure how? Bubble pressure. Okay? So then you have the mole fraction in the liquid phase multiplied by the activity coefficient, right? And then from there, we take the sum and we get this value. And we use the PI sat as well, right? P1 sat and P2 sat in that equation. Once we have that, then I can use modified Raoult's law to find the mole fraction in the vapor phase. Once I have that, then I have x1 and I have x1 and x2, and I have y1 and y2. Then I can find my alphas, right? What's alpha? Relative volatility, right? Either I use, in this case, if you remember, alpha 1, 2 was equal to y1 over x1 divided by y2 over x2. Either I use that, or I plug into this expression what the modified Raoult's law would give me, right? So what is, from modified Raoult's law, we have y1p equals x1 gamma 1 p1 sat, right? So then y1 over x1 gives me what? Gamma 1 p1 sat over p. So either I use y1 over x1, or I can also use these straight into the expression. Assuming, like, for example, I didn't calculate the y's, then I already know the gammas, I already know p sat, right? I know p, then I can, using just the first 4 columns, I can find the alpha. So you don't necessarily need to find the y. If your goal is just to find what is alpha, and why do we find that? We find that to also know if we have an isotrope or not, right? So knowing alpha near the limits, so near x1 equals 0, near x1 equals 1, if any of the values cross the value of 1, then we know we have an isotrope. Okay? So that is that. So you can repeat example 2 from the last lecture, okay, but now using the Van Laar equation, and I have Excel files attached in the Blackboard for you to work on this. Okay? So now we're going to move on to the next model. So we have the Wilson equation. Again, we're going to start off with binary first, and then we'll go to multi-component system. So for the Wilson equation, again, we have the excess energy, Gibbs energy over RT is going to equal to this expression here, where now we have this parameter called lambda. Okay, so 2 parameters, just like the Margulies and the Van Laar. So we have a lambda 1, 2 and lambda 2, 1. The value for this is obtained using this equation here. Okay, so this equation also shows you that these are temperature dependent. Why? Because we have R multiplied by T. The ratio of the volumes here, this is pure liquid molar volumes, for component 1 and component 2, those don't have to be at the temperature of my system. Okay, so this is a ratio. So typically what's used is the values at 25 degrees Celsius. Where do we get those? We get those from tables. Okay, so we'll see that in a second. The other parameter that you need is this AIG or IJ. So AIJ is an interaction energy parameter, which is basically unique for a given binary system. So if you have, ethanol with water, toluene with, ethanol, or whatever other system you have, this value is going to be unique for that binary system. Where do we get that? Also from the tables. Okay, so we're going to have 1 for every component. So you're going to have 1 for component 1, 1 for component 2. So it's going to be A12, A21. All right, so from there, these expressions are derived, and we get the activity coefficients from this equation and from this equation. So they're quite long equations, but all you need in the end is the lambdas and the mole fractions. So once you find the lambda for 1, 2, and 2, 1, then, and you know the mole fractions, then you can calculate the activity coefficients, and then from there you can get the bubble pressure, from there you can get the mole fraction in the vapor phase, and so on. All right? At infinite dilution, so if x1 approaches 0, then we get the natural log of gamma 1, so activity coefficient at infinite dilution is equal to this term, and then second one, this term. Again, just equations that you're going to have available for you to apply, but you have to understand what they are. So here we have the multi-component system, and we have that table that I'm talking about. So let's talk about the table first. So in this table, we have different systems. So here we have acetone with water, methanol with water, and so on. So binary systems. And in those systems, what we have is the molar volume, so V1 and V2. So acetone's molar volume is 74.05 centimeters cubed per mole. Okay, so the units are up here. And these are typically taken at a temperature of 25 degrees Celsius. Then the Wilson equation parameters, right? So this is the interaction, energy interaction parameter. A12 and A21 are given here. Okay, so basically take these values from the table, use them in the equation, then you got your activity coefficients once you find the lambdas. All right, so in general, all right, this is the general form. So the excess energy over RT is equal to the negative of the summation of the mole fraction multiplied by the natural log multiplied by the summation of all the components, in this case, starting from J and so on, and this here is lambda Ij. Okay, so again, this is for multi-component. The one before, you can see how it applies. So this negative x1 is what we see here. Okay, negative x1. Then the natural log of what? X1 multiplied by lambda what? Ij. In this case, I is what? 1. Right? So in the first iteration, this is 1. And then J is 1 as well. So when we have 1, 1, for Ij or I equals J, we get lambda Ij equals 1. So that's why up here, it's just x1 without a lambda, because it's multiplied by 1. Then the next one, so now J equals 2, so x2, multiplied by what? Lambda 1, 2. So this is what we see here. x2, lambda 1, 2. So then if you have more components, it just goes on that way. All right? So this is the multi-component equation. And then with respect to the activity coefficients, we have this expression. Again, follow the same rules for doing the summations. All right, and then here we have the lambda calculation using the parameters that we see here. So for any interaction ij, again j over I, aij, we get the a's from here, we get the v's from here, and you apply the equations. So this here specifically is for binary systems, but if you have multi-component system, then you're going to need another table. Okay, because you need a lot more parameters in that case. All right, so the next model, which is the last one I'm going to present, is NRTL, so non-random two-liquid theory. And this essentially, from the name non-random, it's telling us that when I add two things together in a solution, right, we have non-random interactions. Okay, they're not random. There's some type of interactions that happen, and that's captured by these models. So the NRTL, okay, and the Wilson are more accurate than the other ones that we presented in terms of calculating the activity coefficients. All right, so in this model, again, we have more variables. In this case, we have tau, so tau21 and tau12, and g21 and g12. What are those equal? First, you want to find the tau, then you find the g. Why? Because the g is a function of the tau. How do you find the tau? Parameters from a table. So tau12 is equal to b12 over rt. Where's 1, 2? It's right here. Okay? And then the other one for a binary system, tau21, b21 over rt. Again, b21 is what we see here. Once I calculate those, then I can plug them to this expression where we have another variable, alpha. Where's alpha? Also in the table. Okay? So alpha multiplied by tau12 for G12, plug it in there, in here. You have also the tau, so you do all the math, okay? You find the tau, you find the G's, then you can find your activity coefficients, 1 and 2, using these expressions. So again, lots of math, but it's pretty much straightforward. So typically now, relating to your project, okay, that you have for the course, the models, these models, are built into the computer systems, right? So we don't have to do all this math ourselves anymore. The computer software has it all built in. You just plug in what's your mixture, it'll do the math and calculate your PXY diagram for you. And that's what you're gonna do in the project, okay? And there's a video included in Blackboard that goes through all the steps. So watch the video, and maybe you can watch and do it at the same time. You can, it's just, there is no audio, like it's just like an illustration video. So I don't talk in the video, it's just showing you the computer and what I do on the computer, and that's it. Okay, so follow that to do it. Shouldn't be too long to do, okay? And then make sure, if you have any questions, let me know, but it's all in the video, okay? But make sure you sign up. So you need to sign up to a group, because based on your group number is your actual system. Okay, so every group has a different binary system. Okay? Each group is 2 students, yes. All right. So this is the NRTL model. So now, I'm going to give you guys time to practice all what we've learned. Okay, so I have here practice problem 1, and then 2, and then 3 and 4. So 4 problems in this lecture for you guys to practice, in addition to the problems that we had, built in to the lecture itself, okay? So, and then if you go to the slides online, after the last slide, for the extra slides, I have the solutions to those problems, okay? So practice those.